speeder going 88 miles per hour passes a cop that is going at 42 miles per hour. At the exact moment the car passes, the speeder that is, the cop accelerates at 6.5 meters per second squared. How much time does it take for the cop to catch up to the speeder, assuming the cop maintained a constant acceleration? So this is now a first of a series of questions that's going to get maybe slightly more complicated than some of the other questions we've looked at, in the sense that I'm not just going to be able to take one kinematic formula, make some replacements, solve for a result, but I'm maybe going to have to think a little more creatively, maybe use more than one kinematic formula, or maybe describe, in this case, more than one object. And I think I'm going to start by thinking about this a little bit theoretically, and I'm going to think about the speeder, and I'm going to think about the cop, and how might I describe their position as a function of time. I want to say equations of motion for these two objects because that's a common term that physicists like to use, but based on kinematics. Now, the speeder is just going at a constant rate. So I think if I were to say, I'm just going to use maybe an x, maybe I'll say x sub s for speeder, right? X sub s as a function of time, because I'm liking to use, like, sometimes I like to use things from functions from math, in other words, but it's the speeder is going at a constant speed that corresponds to 88 miles per hour. So I'm just going to use the rate formula for that and say, okay, it's whatever speed that is, and I'm using subscripts to tell the story. I'm using the subscript s to mean speeder. So this is how physicists use subscripts. They're meant to be descriptive. It's, not everybody has to do it the same way. It's kind of like if two people write an essay on the same topic, it really shouldn't be an identical essay for two people, right? When two physicists solve the same problem, they do get the same answer. They may use different notation on the way. Now, the cop is maybe a little bit more complicated to describe the cop's equation of motion. In other words, position as a function of time. The cop, and I'm kind of thinking about, like, you could argue, like, this is like a special case of the first kinematic formula, right? So first kinematic formula has, like, x is equal to x naught plus v naught t plus 1/2 at squared. Now, for the cop, there is no x naught here because we're just talking about the exact moment the car passes. So initially, both of these, I think, are starting at a position that I'm going to regard as 0. So no x naught, in other words. But the cop, when it's passed by the speeder, is going more slowly at a different speed. So that I might state here, instead of like saying v naught t for the first kinematic formula, I'm going to say v c t because I'm describing the cop. But the cop at that exact moment accelerates and continues to do so. So it's constant acceleration, therefore. So the first kinematic formula would say I'm going to add plus 1/2 a t squared. And this is going to describe what the cop is doing for this motion. Now, if I were to try, like, one tool I could use to try to understand what's going on here is to try to sketch a little graph of these two functions. And clearly, for both of them, they're at the way I've set things up. I've kind of said, let's let the origin represent where they are the moment the speeder passes. That's x is equal to 0. And the speeder is just going at a high rate of speed, and it would look like, in terms of an x versus t curve, it's just going to look like a straight line. The cop is starting out slower, so it would have, like, kind of like a lesser slope there, but then the cop is constantly accelerating because of that 1/2 at squared, and so it looks like kind of a parabola there, because this thing is, you see, it is a kind of quadratic in the independent variable of t. And this point right here corresponds on this graph to where the cop finally catches up to the speeder. And since we're being asked for how much time, this is really an intersection problem where I'm being asked for, like, what is this time right here? And so in terms of formulas, I could state that then as, well, really the concept is this function equals that formula, but I'm just going to jump straight into velocity or speed of the speeder times time is equal. In other words, the one function is equal to the other function is how you do any intersection problem. Whoops, that was meant to be a 1/2. And I'm looking for the non-zero time. Clearly the two graphs intersect at t is equal to 0 because that's when the speeder first passed the cop, but I'm more interested in the point where the cop retakes the speeder. So I'm just going to cancel off that time. You're normally not allowed to do that if t is equal to 0 because you'd be dividing by 0. But in this case, that is okay. And my goal, again, is to solve for time, right? So I put that question mark here, but I could also say, I'm doing an intersection problem with that goal, solve for t. So that helps me to remember here that maybe what I'd like to do is, I think I'm going to say, I'm just going to move 1/2 a t over here and subtract v sub c from both sides, which really lets me say, I don't know, I might be doing a little bit much algebra in my head here, but I've got limited space. So the difference in these two speeds, the speeder speed and the cop speed. And at this point, maybe I could solve for time by multiplying by 2 and dividing by acceleration. So I would have 2 times vs minus vc divided by the acceleration a. And then, I've got limited space here, but I'm going to say, so the speeder's speed we were given as 88 miles per hour, which if you do the conversions for that, I have this written down. It's 39.331. I'm going to go at 5 sig figs because it looks like I'm working at 3, and I always keep 2 extra to avoid round off. So that's where I'll round for meters per second. And VC for the cop was 42 miles per hour, which if you do the conversions on that is at 5 sig figs 8.772 meters per second. Okay. And then the acceleration was given to us as 6.5. So if you put those numbers in for these values, I'm kind of running out of space, but in your calculator, you just do 2 times the quantity of the difference of these two numbers, the 39.331 minus 18.772, and then all of that divided by 6.5, and my calculator gives me like 6.3258, etc. But that rounds up to 6.33 seconds. So I'm going to report that as my final answer to this question. Let's check it. Looks like everything worked.